Our next speaker is going to be Professor Lori Tunstall. She is assistant professor at Colorado School of Mines. She has a Ph.D. from Princeton in materials science in 2016. She's doing cutting-edge research on cement and concrete, lowering its carbon footprint. Her talk is entitled The Feasibility of Biochar as a Cement Replacement to Reduce Concrete Carbon Footprint. Thanks, Lori.
Well, it's up. All right, I'm not mic'd, right? Just be loud.
Oh, here, why don't you just use this one?
Okay, I'm gonna put this in here so I don't feel like a rock star. This is snapping. Okay. Can everyone hear me okay? Can everyone hear me now? All right, I'll stand closer to it. Well, it's a pleasure to be here with you all. I want to thank you for just inviting me into your community. The biochar community has been great to be a part of. You all are doing really amazing things, so I'm just very thankful to be a part of it. So today I'll be talking about the research that we've been doing to lower concrete's carbon footprint using biochar as a partial cement replacement in cementitious mixtures. So to start, I wanted to just cover some concrete basics and make sure we're all on the same page and just help guide our discussion. To start, what is the difference between concrete and cement? I hear these terms used interchangeably a lot, but they're not quite the same. Cement is just one ingredient that's used in concrete. So concrete has cement, water, and coarse and fine aggregate. So the cement powder is just one ingredient, so I wanted to make that distinction to start. And then today I'll also be talking about concrete and mortar. So I wanted to call out those differences as well. So the real difference between mortar and concrete is that concrete contains coarse aggregate and mortar just has the fine aggregate. And the reason why I wanted to make this distinction is most of the work that we've done in my lab has been on mortars. The reason for this is that we can just do a lot more reproducibility with the same amount of materials. It just takes a lot less materials. And we've demonstrated, and others have demonstrated, that the properties and the trends that you see with mortars is the same for concrete. So there's no loss there, but I'll be using these terms kind of interchangeably, so I just want you to be able to track along. The laboratory tests we've done have been primarily mortars, but there's applications to concrete. I also thought it would be prudent to cover a little bit of cement chemistry. I'll mention that in the presentation as well. So when we put a dry cement powder into water, we get a chemical reaction. It's something called a precipitation reaction, where we dissolve the cement powder, the ions go into solution, recombined with water molecules to form hydration products. So we call this cement hydration. The two main hydration products that we get from this reaction is something called CSH, it's calcium silicate hydrate, and calcium hydroxide. The calcium silicate hydrate is, or CSH, is the glue that binds the concrete together. It's really, when you think of concrete and all its engineering properties, this is why it has the properties it has. It's almost all due to the CSH formation. In contrast, the portlandite or the calcium hydroxide is mostly inert. It provides some strength because it's a solid, but it's nowhere near the properties that the CSH contributes. So that brings me to another chemical reaction that often happens in concrete systems, and that's a pozzolanic reaction. With a pozzolanic reaction, you have a pozzolanic material, so it's something that's got reactive silica, so you have silicon ions dissolving in solution, and those silicon ions react with the portlandite from the cement hydration reaction and combine with water to form more CSH. So pozzolans are great because it takes this inert material, the calcium hydroxide, combines with silicon ions, and then forms more CSH, which again is the strength-producing material that gives concrete its engineering properties. So we really like that in concrete systems. We use pozzolanic materials pretty regularly, mostly fly ash, but also slag, silica fume. These are commonly used materials in concrete to reduce some of the cement and also enhance some other properties like strength. So from the title, you know what we're doing, what the motivation is. We want to reduce the carbon footprint of concrete. So what is the problem with concrete? You might be aware that concrete's responsible for about 8% of global CO2 emissions. So it's a big contributor. That's not because concrete itself is super inefficient or it's not a green material. In fact, if you replace it with any other building material, the problem would be worse. This number is really because we just use so much concrete. So it's the second most consumed material on the planet, second only to water. So huge supply, and that's where we're getting that 8% number. And that's really tied up in the manufacturing of the cement powder itself. So when we manufacture cement, we mine limestone, we take it, heat it up to get free lime, and that's what we want in our cement powder. And so what you can see here from this chemical reaction, you do that and you kick off CO2. So it's basically a 1-to-1 ratio of CO2 for every molecule of free lime that you get. And so that adds up quickly. And we get about 1 kilogram of CO2 for every kilogram of cement that's produced. So what do we do to address this? Well, there's a lot of new technologies out there. You'll probably hear about some of them in the news. Some of them are trying to replace the cement binder itself. So using something else. If this is the basic recipe to produce cement, then let's not use cement. The problem with this is that most other materials and solutions really can't meet the supply of the concrete industry. So as much as we want to try to use these greener alternatives, we really just don't have the supply of raw materials as abundantly as we do limestone. So at least in part, this is going to be around probably forever. So then, knowing that this is going to be a part of the solution going forward, how do we work with what we've got? So our approach in our lab has been to replace some of the cement in mortars or concrete with biochar. So we reduce the demand for cement, and we're also replacing it with a carbon negative material. And so some of the goals of my group have been to see what properties of biochar we need to control to have beneficial use in concrete. So we've looked at a pretty broad range of biochars. We have shown 16 here. We are always looking at more, so we kind of just cut this off eventually. But what we have found is that compared to our control sample, all of the biochars we've tested actually improve strength or keep it the same. So most of them, as you can see, improve the strength compared to our control, which is, can you see my card? Yeah, so which is the sample here. So we've looked at hardwood feedstocks, softwood feedstocks, agricultural feedstocks, and as you can see across the board, different pyrolysis conditions, we are getting pretty good properties with the concrete. And I wanted to point out also that this is with 10% cement replacement with biochar. Why 10%? Really, it's because the sources of biochar we had were pretty varied in how much quantity we had, so we wanted to test them all at the 10% level so we could be consistent. We have demonstrated we can go up to 15 and even 20%. And most recently, I think we've tested up to 35% cement replacements with biochar, depending on the type of char and the mix design control. We've also recently been doing some permeability testing. So the way that we're measuring this is basically a measurement of the depth of water penetration when a sample is pressurized underwater and allowed under those conditions for 3 days. So on the furthest left bar here is our control sample. So that is just a traditional concrete. These are actually concrete samples. And we found a depth of water penetration of 18 millimeters. When we add biochar, we consistently see a decrease in permeability. So from left to right, we'll see there's 4 different biochars here tested and at 3 different concentrations. So we've got a 5% replacement, 10% replacement, 15% replacement. You can see each biochar affects the permeability a little bit differently, but consistently we see a decrease in permeability with increasing biochar replacements. The implications of this are huge. So in the concrete industry, when you're trying to make changes, one of the things that you have to do is demonstrate that the change you're making does no harm. And some of the ways that we test that is strength. So I showed that in the previous slide. Other ways we test that is on durability. But the problem with durability testing is that it takes a long time. And oftentimes we need we need answers faster before we can implement it. We don't want to put it out, it's kind of a chicken or egg situation. You don't want to put it out and see how it lasts if you know it's not going to last, right? And so this is a good indicator of how it'll perform for different concrete degradation modes. Almost all the ways in which concrete fails is due, at least in part, to water ingress inside the concrete. So if we can make it less permeable, then it should be more durable as well. So this is great news in that we can anticipate that the biochar cementitious composites will also be more durable. We've also done some testing to see how compatible it is with other commonly used mixtures like fly ash. So remember, that's one of those pozzolanic materials that we use in concrete, and it's very commonly used. So we want to make sure that it's compatible with some of these other solutions. And what we found is that the biochar is really useful for accelerating the strength gains in these composites. So walking through from left to right here, we'll just focus on 28 days. We've got the control mix, so that's no replacements of cement in this dark gray bar. The dotted bars each have cement replaced with 10% biochar. And then the light yellow is 20% of the cement replaced with fly ash, and then the gold is 30% with fly ash. So, and then this is a combination of both, right? And so what we find is when you just replace the cement with fly ash, 28 days, that's typically your ultimate strength for a traditional concrete, we find that the fly ash is much lower in strength. And this is typical because that pozzolanic reaction takes time. So when you incorporate pozzolanic materials, you typically don't get your ultimate strength until maybe 56 days. And this often limits how much of the cement we can replace with pozzolanic materials because we're driven by construction schedules. We can't wait an extra month before we can open up a project or get to the next part. And so we're limited in how much of the cement we can replace with pozzolanic materials, in large part because of the rate of the strength gains. What we find is that when we combine this solution with the biochar solution, so now we've got 30 to 40% of our cement replaced with some combination of the fly ash and biochar, we see increased strength gains compared to the fly ash solution alone. Now, we would anticipate also that this would continue to strengthen up to 56 days, just like most pozzolanic materials. And so this is, again, great news because we can now use some of the solutions that we've already been using, but accelerate the strength gains. So it allows us to potentially replace more of the cement with fly ash by adding some additional biochar, which is carbon negative. So it's a win-win in terms of reducing carbon footprint. And you'll see here that this mix shown with the dark yellow and the dotted is we're already at a 61% carbon footprint offset. So that's not our goal. Our goal is neutral or negative, but this is a huge win for the concrete industry, especially if you think about how much concrete is produced, reducing the total CO2 emissions by 61%. I mean, if everyone adopts this, right, we've gone from 8% of global CO2 emissions to half, or less than half of that. So what kind of biochar works? And I think that's probably what's mostly of interest to all of you. We've tested, as I mentioned, several types. 16 are shown today. And this is a little bit more details on that. So we've done softwoods, hardwoods, agricultural feedstocks, different pyrolysis types. So fast, slow gasification, different temperatures. And really across the board, we found that all of them are feasible. This is another bit of great news for the concrete industry because, as I mentioned, the supply for concrete, I mean, it's staggering. I think it's hard to kind of, if you're not in the industry, it's hard to kind of appreciate just how big it is. But I mean, we're dealing with like millions of tons from just locally, right? So it's a huge industry. So to meet the demands of the concrete industry, if we're really going to reduce concrete's carbon footprint with biochar, that's a huge demand that we have to meet. So it's good news for the industry that we can seemingly tolerate a large range of feedstocks, pyrolysis conditions, pyrolysis temperatures, or pyrolysis methods, and get biochar that's usable for concrete. However, as you saw with the strength data, not all biochar is created equally. I mean, it seems like some of the biochar does improve strength more than some of the other biochars. And this is important because feasibly that means that we could replace even more of the cement with those types of biochar. So what's important? We've done a pretty thorough statistical analysis and found that there are 3 variables that we really want to control in our biochar. And those are ambient saturation percentage, I'll explain that more in a moment, soluble silicon, and our oxygen to carbon ratio. I'm realizing this PDF transformation did not work well, so I apologize for that. So that's those are our 3 variables that we need to control. Soluble silicon, I mentioned that already. That's predictive of the pozzolanic reaction, so that one makes sense and why we want the most soluble silicon we can. Oxygen to carbon ratio, that's well known to all of you. And then it's the ambient saturation percentage. We're defining that as basically the percentage of the total absorption capacity of the biochar that's already occupied by water under ambient conditions. So basically it's giving a measure of how much of the biochar absorption capacity is already occupied and how much is left for additional reactions in the cement system. So really, given that this is such a big predictor of the strength, what that tells us is that one of the main ways that biochar is affecting the strength of cementitious composites is through a reduced water-cement ratio, something called like an internal curing agent is what it's acting as. So basically what that means is that you're mixing everything in with water. Depending on how dilute your concrete system is pretty predictive of what the final strengths will be. It basically gives you an indicator of how much pores will be left in the concrete once it hardens. Now, if you can throw in an internal curing agent, you're taking out some of that water that gets released again for additional reaction later, and you get a stronger composite. So that number is really indicating that that's one of the big roles that biochar plays. And so we want to try to maximize that impact. So what is the feasibility of a carbon negative solution? In the concrete industry, cost is king. So, I mean, I think that's true everywhere, but it's especially true in the concrete industry. I mean, with the quantities people use, if you can save a cent on a yard, that adds up to a big cost savings down the road with the volumes that's produced. And so from folks we've talked to, as much as everybody likes the idea of a carbon neutral concrete, nobody's going to pay for it, not yet. So potentially this can change with different governmental regulations and incentives, but right now we really need to get a solution that's at about cost parity. Maybe we can handle a little bit of a green premium, but certainly not much in the industry as it stands. And so I've put together just some estimates here on what some cost projections would look like depending on the cost of biochar. And this is where I think the concrete industry needs you all to come up with solutions where we could sell biochar for something closer to $150 per metric ton. That would get us at cost parity to cement. So if we can replace some of the cement with another material that is carbon negative and the same cost, that's going to be a pretty easy sell to a lot of people. We've demonstrated that for this carbon neutral solution, so replacing 33% of the cement with biochar, we would get a cost that's about 118 to 172% of a traditional mix, and we would have a strength that's just about the same or a little bit better. And so that's great that we have a carbon neutral solution that can work, but we really need to get this number down further. And you can see what's really driving up the number is the cost of the biochar. We're also looking at other solutions. We don't have strength data on that yet, but this solution potentially would be if we could get the cost of the biochar at this lower number, the $275 per metric ton, we could get a cost parity solution that would be carbon neutral or slightly negative, actually. So assuming that the strength comes out okay, then we've got another solution that could move forward in something cost parity and for the industry. So I think this is where we really need to work together, building on our expertise from the concrete industry and the biochar industry to be able to come up with a solution that can get to carbon negativity, similar performance metrics for the concrete, and hopefully cost parity. So I wanted to thank my students who have done most of this work, so my PhD students, Julia and Adam, and my undergraduate researcher, Dylan, and I also gratefully acknowledge the funding support from NSF, Mines Foundation, and Colorado Advanced Industries Office. Thank you so much for your time.
Thank you very much, Laurie. Now we have some time for questions. Right there?
Yeah. No, we make our own references. So we try to keep the mixed designs as similar as possible. We have certain controls in place so that we can be confident that what we're getting is a valuable control. Yeah, that's important for us because, as you might know, that depending on how you're making just a traditional mix can vary quite a bit in your strengths. So
Can you repeat the question?
Oh, sure. So the question is, the question was, given that concrete is 10% cement, then you're replacing 10% of 10% with biochar. Is that right? No. So it's a weight percentage, first of all. So we're replacing the cement by weight. I think the volumes, and somebody else with, I don't know, might call in John there, for the concrete volumes. We don't make a lot of concrete. I don't remember off the top of my head what we use, but that seems light. I think the numbers would be higher there. And then it's a weight percentage that we replace. So what's key is, in this case, it's not so much the recipe that we're toying around with. What we care about is the carbon emissions. So the cement is really the big hitter of CO2 emissions. So when we're talking about reducing the carbon footprint of concrete, it's really the cement that we want to target. Yeah.
Hello. Yeah, I would be doing an injustice if I didn't introduce myself. So I'm Chaiwe from Zambia, coming all the way 30 hours back.
Welcome.
Thank you. And my question is focused on the feedstock that you've used. It's A-grade feedstock rather. And back home, we've tried and experimented with fecal sludge as more of a less in quality biochar. And I think that's important, especially from the price point of view, because you're not competing in terms of usage with better products per se. And what we discovered is the quantities and the qualities of the fecal sludge would influence what the result of the strength of the blocks that we developed as a result. And one of those things is high sand content in the fecal sludge that we're getting out of the pit latrines. And so it would be great to look at that avenue as well. We know that fecal sludge, based on where you're getting it from, has high toxic content. And so it influences the result as well from a properties point of view. And we also tried fecal sludge with plastic to get a fecal sludge-based plastic blocks. And when we added fecal sludge, it solidified instantly versus biochar that's made from plant-based feedstock. So properties there really differ, and it would be great to hear from others if there's any examples that are similar. But I think it's great to really try with fecal sludge that is not A-grade per se. Thank you.
Yeah, I totally agree. I think that's a great suggestion, and that's something that our group wants to look into more. We want to, we've basically been testing everything that people have sent us. So if anyone wants to send us stuff to continue testing, we'd be happy to accept it and fold it into our broader study. But I agree that that's an important waste stream and feedstock that we haven't explored yet, but could have big implications on lower costs and still potentially could be tuned for use in concrete. As we found, we can handle a pretty wide variety with a good mixed design and still get good results.
Can I just ask a question to the person who just spoke? Do you have any published information, articles or anything on that? Do you have published information?
We don't have published information. We just started working with it. And one of the things we really want to do deliberately is engage and partner with interested institutions. Back home, there's not sufficient access to labs. And so if we can partner with an institution that's willing to look into our work, I think that would be much appreciated. Then we can get into publishing. Yep. Thank you.
Thank you.
Hi, Josiah Hunt here, Pacific Biochar. We sent you some samples.
Hey, Josiah.
Yeah, thanks for the great work and great presentation. I just wondered if you had anything to say about how does this actually get implemented in the commercial industry? I know that it's really important to get it in the specs. There might be permitting issues. With the concrete, we have different layers. We have concrete in your parking lot, but then you have vertical stuff. And so I know there's a lot of layers to the permitting process. And I just wondered if you could speak, where can we get started and how long will it take?
Yeah, those are great questions. Those have been a lot of the conversations I've been having recently. I think ASTM is a great place to start. There are no ASTM specs that this fits neatly into. So from talking with decision makers, it seems like one of the best ways to start is basically to test everything and make sure that it doesn't do any harm. And so there's one spec that's designed, I believe it's 1709, C1709, that is focused on analyzing alternative supplementary cementitious materials. So that we wouldn't really consider biochar as an ASCM, but it's a starting place in just having some comparisons so that decision makers know what properties it has compared to other properties we care about and can make a spec that's specific to biochar. So that's one of the things that we're really looking for. We're looking for funding to do that. So if anybody has a free few $100,000 they want to send us, we'd be happy to do all of that testing. So that's one of the things that we think is really critical. And then also partnering with ready mix suppliers who are willing to just test it. We know that the ASTM standards aren't quite enough, for example, to get engineers and architects to buy out on it. They want to see what it actually does in real conditions. Nobody wants a liability of a new material. So if we can get progressive ready mix suppliers to test some samples for some like low risk applications, I think that's another important step just to put a mark in the timeline of, we've had this stuff out there for X amount of years and it's holding up great. So I think a combination of ASTM standardization and just some real field pilots would be the next important steps.
We have time for 2 more questions. Cool, thank you. Yeah, I'm Bjorn Becker. I just want to find out the water to cement ratio. What did you find there? What was your biochars moisture content and just how was that affected?
Yeah, so those are great questions. So the question was water to cement ratio. As I mentioned, that really controls a lot of the strength properties. We are not counting the biochar as part of our cementitious content. So when we do our water cement ratio, we're really basing it on the cement content that's in there. So if we reduce the cement content, we have a lower all around water demand. We are trying to compensate for ambient moisture in the biochar. So we tune for that. So that will vary slightly depending on what we measure for the biochar. That ranges a bit. We'll have a publication out shortly that you can check out that has all the details for the biochars we've tested that I've just presented on. So it does vary a little bit, but not as much as you'd think. We were kind of surprised that it was a pretty tight distribution of variation there for just like ambient saturation. Is that all your questions? Okay.
One more?
So what was the moisture content of the carbon that you tested? And was the numbers that you gave on the price that you're trying to get the carbon down to, is that on a dry ton basis?
Yes, it's on a dry ton basis. And the percentages we got, I think the highest one we tested was 20%, but that one was an outlier. Most of them were tuned within, 1 to 4%. And that's, just ambient saturation. So we're in a pretty dry climate in Golden. So potentially if you don't have storage controls and you're in a more humid part of the world, that would vary. So it's something that you would have to test for, I think, to use and compensate for correctly. Similar to what we do for aggregates already in concrete. I mean, that's something that you want to test before you're using it so you can adjust the water of your mix.
We can take another question. We have more time.
Yeah?
Just wanted to touch on one of the aspects you deemed as important. I've got a ton of questions for you, but I'll keep it to one. You had mentioned milling as being important. Do you have a particle size distribution where you found effective utilization and effective incorporation? That can be a fairly significant cost if we're talking about fine milling.
So well, we haven't done a study on this systematically to purposely alter it to see how it's affected. We have found that it mills really easily. So all of the biochars we've tested, we mill for about 5 minutes, and it goes down to an average particle size of 10 microns within 5 minutes. So it's really not an aggressive milling operation. It doesn't seem to be time consuming or energy, very energy consumptive. But and then we get to the 10 micron particle size pretty easily. So we have not controlled for particle size distribution. We kind of just have been using what we get after the 5 minutes of milling. We did test all the particle size distributions, and that'll be in that publication as well if you're interested. But it's a fairly tight distribution, and it's all below the cement powder. So that's typically what we want, so that it's not, you don't have these big inclusions that are affecting the strength.
Well, thank you very much, Lori. We appreciate your talk. I think that was very interesting. And if people want to get a copy of your presentation, that will be available later through the USBI conference.
Yeah, perfect. I also, unfortunately, have to be heading back home shortly after this session. So I'll leave some business cards up front here if anybody else wants to reach out to me and ask more questions. I'm happy to answer questions, send you the manuscript, slides, whatever. So I would really love to collaborate with all of you on this important question.
Thank you.
Biochar.org appreciates the support of our sponsors, exhibitors, presenters, and attendees. We look forward to seeing you at our next conference in September 2025.